So it captures everything that is on the screen, and then of course it captures the audio. So I'll remain close to here, and hopefully it will be beneficial for you guys if you need to go back and review some of the concepts that we're talking about in class. So I'm an electrical engineer by background, but I'm really very passionate about multidisciplinary work. I actually do a lot of mechanical and some chemical work as well from on a research perspective and commercialization. So I'm very passionate about trying to commercialize technology and push things to the next level. I was able to start, 2 companies. They're not failing, so and I'm very proud of some of the stuff we're doing. So I'll show you something we're doing to prove that Ahmed's not alone. So here, so so for example, Modus is one company I started 2 years ago with a friend of mine, and for 2 years, again, starting something is not easy. So what we've been doing is designing drilling tools, and so we design and manufacture and do services on drilling tools. So which in the oil and gas arena, there's a lot of chemical stuff happening as well, right? So drilling fluids are a lot of chemical stuff. We don't do any drilling fluids work as such, but so we buy our current drilling fluids. But I'm doing a lot of work on chemicals, chemical materials, or materials that we can coat fiber optic cores with, for example, to exchange their absorbance properties. So we're trying to develop some, distributed sensors for pressure, for example. Currently, there are no distributed pressure sensors, and this is something we're working on as well. So the idea would be to develop materials that we can coat fiber optic cores with that would change absorbance properties with pressure and be able to manufacture that in a distributed fashion. So that's some of the chemical stuff I'm working on. We've been working with another company here, for example, on chemical material elastomers that we can use to plug fractures in wells. So a lot of chemistry there as well. So I think there's a lot of value in people working together. That's what I'm trying. The message I'm trying to deliver here is, us electrical engineers or chemical engineers or mechanical engineers working alone is not very critical, and that's where the research breakthroughs are happening. Multidisciplinary type work, right? So I encourage you to push yourself to to learn about other disciplines. So chemical guys, fine, you're learning here about electrical engineering. I don't know how much you learn about mechanical engineering. I'm sure you do. I mean, the good thing is there's a lot of thermodynamics in common that you probably take with mechanical and maybe with petroleum engineering, right? And heat transfer, that's probably something that you probably take and they take as well. Some fluids work, mechanical and petroleum and chemical guys take as well. So there's a lot of overlap, more than you think of, right? So and it's very good. I mean, this is where this overlap happens. Is okay. These guys understand the same things that you're talking about, but you can help enhance or motivate or push things a little bit further in your direction, right? And that's what we've been doing here. So I'm an electrical guy. I work on sensors, for example, and electronics for drilling applications and oil field applications. So, with my team, my team is a lot of mechanical engineers. So we have mechanical engineers, we design and manufacture all of this stuff. So I had to learn a lot about mechanical engineering, design, manufacturing, etc., etc. By background, it helps. So I used to work for Schlumberger for 7 years. So I have that sort of, interest in oil and gas and multidisciplinary work. So our team at Schlumberger used to be 14 guys, and we used to be from 10 different countries, and everybody was addressing a certain aspect of the project. So we had mechanical engineers, electrical engineers, computer engineers, sensing/physics people, and a project manager. We were all working together, and you had to get the exposure that, to what everybody else is doing to be able to understand and to be able to push and lead the project, right? So that's the objective of what we're trying to do here. I'm not trying to really make sure that you can quiz an electrical engineer after you graduate on Ohm's law or how to solve a circuit, right? But the ability to understand, what these guys, electrical guys, do and why they do it is important. So we'll try to relate what we're doing as we move along to some practical applications. I will try. And I hope you find it interesting. Okay, it's learning about another discipline. Maybe a little bit boring if it's something you have to do, and you don't see why you really need to do it. Right? So I understand. I took chemistry, for example, in the first year of engineering school in my undergrad, and it's the only course I did not do well on in my 5 years of engineering. So, but now I appreciate it a lot more after having to interact and work with chemical engineers and chemists, right? So, and the same thing with mechanical engineering. I used to love mechanical engineering anyway, but so we used to take, I took machine design, I took theory of machines, I took thermodynamics, and I took a lot of mechanical engineering courses, which were, outside the electrical engineering discipline. Because of that, you're able to work and interact and even invest all my funding and my money into something like this, which has a lot of mechanical engineering components. So we successfully field tested our first product, which is the Almas drilling bits. And if you look at what we have here, this is the rate of penetration. So it's the rate of penetration of the drill bit into the ground. So drilling speed basically, and in the whole field, which has many different wells, we drilled the Gazara 6 well, which had the rate of penetration of 21.2 meters per hour, which is the second highest rate of penetration in the field. So this is just happening. This just happened last 10 days ago, basically. So I'm very happy with this, and I wanted to share it with you. But the idea is, it's multidisciplinary work is important. That's the moral of the story. So we can end the class here, because today was just a motivation of why you should be interested in 215. No, I'm just kidding. So we'll have to skim through the syllabus as well, as a secondary thing from doing things. So the course will cover a couple of things. Actually, it will cover it's the first time for me to teach this course, right? So when I looked at the syllabus, I was like, wow, they have to learn all of that. So I was a bit shocked, because I think it's like, okay, you're learning everything that the basis of everything in electrical engineering. So it's a bit interesting. It's for me to teach it for the first time, because I was like, wow, too much. But so the idea is not to drill you on a specific component of it. Okay, so the idea is to be able to help you capture the concepts. And some of the stuff I'm pretty sure we covered in high school. So some of the physics in high school. How many people did IB, for example, or AP or A levels? Okay, so we can actually go home. We can actually stop for the half the semester. Like stuff like Kirchhoff's voltage law, node equations, and nodal analysis. I know that if you did IB or AP or something like that, or AGCSE, A levels, then you've covered this material. So, which is good review. So to be good review. The idea is actually what we want to do is actually try to tie it into applications. So if we tie it into an application, you will have a better feeling of why in the world is he going through this again, right? So that's hopefully what we'll try to do. So there are other sections of this course being offered. We will have different exams. So Dr. Robert will be handling his own exams. I will be handling my own exams. We will try to sort of keep the topics in sync. So we will cover certain topics in the class, and his sections will cover similar topics. We will cover similar topics in class. We are basing the slide set on the same initial slide set, but he's making his own changes to it and twists to it. So that's that's how he's going to do it, and I will do the same thing. I will talk about different applications. I will have my own twist to the slide. We will have a separate exam. That's what we're going to do. The homeworks, again, actually let's go through the syllabus and then we'll continue. So the prerequisites for this course, you all have these prerequisites. So the idea is to understand the basics of electrical circuit analysis and electronics. Why is electrical circuit analysis important? I just finished teaching the seniors in electrical engineering power systems, the first power systems course. And this is the circuit that we ended up the first class with, right? Does this look similar to something you've studied in electrical circuits in physics, for example, when you were doing your IGCSEs, A-level, IB, etc., or not? Very similar, right? Very similar. So this is what I was talking to the senior electrical engineering students about in the morning. This is how we represent the power system. This is actually a big power system, a generator, maybe a representative of a small industrial plant in Ras Laffan, right? So electrical circuits is actually the basic, and the only prerequisite for the 459 course, which is the electrical power systems course. So it's the senior electrical power systems course. The only prerequisite for that is actually 214 or 215 course, right? So the 214 or 215 course, which is basically stuff that it's the extension of what you studied in high school for us in an electrical circuits perspective, is really the basis that you would need to go and understand how to build and design power systems, right? So here is something that they came to the class, they don't know what they expect. And the prerequisite is 214, and they are seniors in electrical engineering, and this is a course on power systems, right? So what we're doing in that class is, again, taking an industrial facility. For example, let's say an industrial facility is composed of, let's say you have a generator. Everybody knows that to generate power, you need an electrical generator. Right? It's some kind of machine, right? You've probably studied DC machines when you were in high school, right? So a DC machine is a type of generator or a type of motor. It can operate as a generator or a motor, right? If you put in a prime mover, if you connect its shaft to a prime mover, right, and you spin the shaft, do you see voltage at the terminals of the machine or not? Physics. Remember physics? If you have a coil like this, and this coil is spinning, and there's a magnetic field, right? If you spin this, if this coil is stationary, then nothing. If you measure here, you put a multimeter or a voltmeter at the terminals of this turn, you'll measure nothing. Even though there's a magnetic field. This magnetic field may be due to a magnet. Maybe let's say you have a north here and a south here. So the magnetic field is constant, right? It's a constant, it does not change with time. And the coil is stationary, right? What if I turn the coil with a prime mover? I have a shaft outside, I'm going to turn the shaft. Right? So it's turning that coil. What's going to happen is that magnetic field that is going to link this turn. So this is one side of the coil, this is the other side of the coil, right? So now there's a constant magnetic field linking this coil, meaning intersecting with it with the plane of this turn that I have. The turn is here, and this is the direction that's perpendicular to this turn. The magnetic field is constant with respect to one of this turn that I have here. What if I turn this thing around? The vertical component of the magnetic field is now going to be, or the component of the magnetic field that is perpendicular to the plane of the coil, which has now turned, right, is this one, correct? It's at an angle since the coil turned. This magnetic field that's at that angle is composed of what? Is generated from this original magnetic field that does not change position, right? These north-south magnets here are not changing position. I said these are fixed, right? So these are fixed, but the coil is turning, which means that the perpendicular component to that turn, which is what is in charge actually to generate the voltage at the terminals, will change. It's seeing a different magnetic field value, right? So, and if I turn it perpendicular, so if I have the magnets like this, and the coil is, actually like this. This is one side and this is the other side, right? Is any of the magnetic field actually going to cut the area perpendicular to the turn? Nothing. So this turn will not even see a magnetic field, right? So in one position it's seeing a full value, one position it's seeing 0. So if you turn it, at different angles, it will see different values of magnetic field, right? So if you go back to Lenz's law, if you remember back in physics, you heard something, an equation that's can be written like this, right? E equals n d phi by dt. Right? This is an equation you probably heard of some time back. What does this say? It means that if I see a time varying magnetic field, if this time varying magnetic field actually links a certain number of turns, n, let's say 1 here, right? So time varying magnetic field linking a turn, then there will be voltage generated across that turn here. Right? So now I have voltage generated across the turn because I had a prime mover that turned this thing around. How does my circuit respond? Back to your physics as well. If you have a conductor with current and a time varying magnetic field, what will develop at the conductor? Now I have current. You have a conductor with current that is moving in a magnetic field. what will develop on the conductor. Now I don't have a prime mover, right? I'm just saying I have a conductor with current. Somehow I put current into it. So remember, before I had force to turn the turnaround. I did not have current. I had force input, turn this coil around, that intersects on the time which created a time varying magnetic field intersecting this turn, and hence created a voltage. If I connected a circuit at terminals of that voltage, I would have current flowing, right? When that current starts flowing, now it's something, it's as if I have something opposite, right? Take a turn, take this one turn and put a voltage across it. Take a turn and put a voltage across it. What's going to happen? Current will flow. If current flows in this turn, and you have a time varying magnetic field, these magnets are now not stationary, they're moving around. What's going to happen? If you have a turn and you push current through it, it's going to create magnetic field around it. Right? Remember right hand rule, left hand rule, all that kind of stuff? Any piece of wire with current flowing through it will create a magnetic field around it, according to the right hand rule. Correct? Now I'm saying, okay, I also have a time varying magnetic field in which this thing is placed. So these magnets are moving them around. So what's going to happen to the turn? It's going to what? No, you already induced magnetic field, because here I'm saying I have an external source and I'm putting current into this turn. Now I'm not waiting for the prime mover to move the turn in a stationary magnetic field, and hence when it rotates it sees a time varying magnetic field and hence sees a voltage. No. Now I am putting current through, as if you have a piece of wire with current flowing through it in a time varying magnetic field. The reverse will happen. I don't have force coming in now. But in this case, force will be generated. Right? I'm sure you'll go back and remember that you have a piece of wire in a time varying magnetic field, you will see a force. Right? You probably will remember that. And that force on current is flowing in this direction in this wire, and then flowing this way here, and then this way back here, back to the source. Right? Current flows from the source, one of the source terminals, it has to go back. Current goes back to where it comes from. Current is very well behaved. It does not go where it did not come from. Comes from home, go back home. There's no going to the gym in the middle and stuff like that. So it will come back to where it came from. So if I don't put that, and this happened because of the prime mover. Now I remove that prime mover. What's going to happen if I put that current in a time varying magnetic field? Force will develop. Right? It's either you put in force and get power, or you put in power and get force. Right? And one is a motor, and one is a generator. Right? Generator, you put in force, you generate this voltage, and when you have this voltage in there, you connect the electrical circuit, a load, and this load will draw a current. Right? When this current starts to be drawn, you start drawing this current, what's going to happen? There will be a force generated. Because again, you cannot have a prime mover spinning the rotor, assuming the rotor is lossless. There's no mechanical. The bearing guys did their job. The mechanical guys did an excellent job, designing magnetic bearings, that have no losses at all. Lossless magnetic bearings, for example, levitated and all that cool stuff with zero loss. Then what happens if you spin this thing, you spin a shaft and there's a lossless thing that's carrying this shaft in the air. Is it ever going to stop? It will never stop. And that's why when current starts flowing after you connect the circuit, there's a force opposing that force that you put in. That's generated. That's balancing things out. And that's where, okay, I balance things out. I put in a certain force, and the generator is responding with force and as feedback. It's like running together. Two people running together, right? If somebody is running very fast and somebody is running very slow, they're going to drag them. They will drag them back. But if you both try to run together, then you may be both contributing. You're both generating power. If one person is slower than the other, what's going to happen? You're pulling him or her, right? The faster one is pulling the slower one, for example. So there's a action-reaction sort of thing, like the laws of thermodynamics and like the laws of mechanical systems. So they're all the same rules and laws, and there's always a reaction to the action that you've taken. So the reason we study circuits is really not to bore you with Norton, Thevenin, blah blah blah, but to tell you that really a power system, the electrical engineers, what they do is take a big power system, which is, again, a generator, which is the discussion we were discussing now, for example, and then transformer, and then these overhead lines that these towers that carry transmission lines that you see while driving. These towers are nothing but cables. These cables are nothing but impedance. Again, they're an inductor, resistor, and have an equivalent capacitance as well, right? So we take that and come up with a model for it. It's either there's only three elements in electrical engineering: R, L, or C, right? So we will take any component in electrical engineering. That's what we studied in the 459 course. Take it and represent it as an R, L, or C, or combination of them. Okay, and then we have what? We have, for example, a load. This is your house, my house, this building, whatever. This building is drawing a certain amount of power. So I can represent this as a load. What is the element in electrical engineering that draws power, consumes power? Well, resistor. Resistors are elements that consume power, right? So mechanical or a fluid sort of analogy would be you want to move water from one area to another, right? The channel that you're moving the water through, the water is the electrical current. The channel that you're moving the water through, is this lossless? There is friction, so the friction will cause what? Some pressure drop, some losses. Because that means you have to actually push the water through. You cannot just, have a reservoir here and then assume that the water will flow there with the same flow rate, for example, right? For you to maintain the flow rate, you have to have a pump that has certain pressure, right? Because that pressure value, there is a pressure drop across the channel that you have to compensate. And then the water or the fluid will reach whatever you want it to reach, for example. So, the fluid analogy for a resistor would be that, the channel, for example. And then that's only that's similar to the transmission line resistance. That's the medium where that's transmitting the power to the electrical grid, right? That's the medium that transmits the power to the electrical grid. That's a resistance here, right? That's going to be burning some of the power off. Okay. What else is happening in that channel? Typically, when you start, you will have to, for you to send the power through, you're going to have to fill the channel first. Right? You're not going to turn on the water and then it's going to end up there. The water has to flow and fill up that channel for you to be able to move water to a different location. So that's sort of a energy storage element or model or component that you have in the system as well, like a storage tank. A storage tank, you need to fill it up before it has a certain water level. Right? So you can think of the current as the water that's flowing. You can think of the pressure drops that are caused by the channel, for example, as these resistances that we have in there. And then there are certain time constants in fluid systems. For example, you're filling up a tank. Filling up a tank until its voltage rises, for example, is similar to a capacitor being charged. So charge is accumulating on the capacitor's plates. Voltage will rise. The voltage value is like the value of the level, the height of water in the tank. Height of water in the tank is like the value of voltage. Capacitor voltage cannot change instantaneously. Exactly the same as water level in the tank. Cannot change instantaneously. You actually have to fill the tank for the level to change. So that's like a capacitor. How about in the resistance is easy. Resistance is anything that has loss. So for example, in a chemical process, you want to heat something, right? So that energy that you're going to dissipate in heat, is going to have to come from somewhere, right? That somewhere is going to, it's a dissipation of power, right? That's what we can represent as an electrical resistance. So in a fluid system, it's maybe the channel impedance. Or what else? Can you give me another example? Mechanical system, for example. The analogy for the resistance. Yeah. heat transfer, for example. In heat transfer, the resistance to heat transfer, right? For you to dissipate heat, right, from one location to the other, there will be an impedance to that heat flow, right? So in this case, heat is what? Heat is like the current. Heat is like the current, and then the thermal impedance to that heat flow is the resistance, right? So, and then the temperature would be the voltage. Do we agree? So let's say here, for example. So I will have a source of heat. I will represent as a current source for current, and I would have different resistances here. So this is my source of heat. Let's say you have a certain value of heat that's generated by the process, right? You want to know how to design the heat exchanger that you're going to be putting in the process to be able to dissipate this heat, for example, right? So you have one temperature value here. Let's say this is ambient temperature, T ambient. And you have here a device that you want to design a heat exchanger for so that its temperature does not go beyond 50 degrees C, for example, right? And then you have many thermal resistances in the path. So you have a thermal resistance from ambient. So if this device was open to ambient, its temperature would be the ambient plus what? If I have a device here who's generating some heat losses inside. So I have something burning inside here, like some process that generates heat inside, a chemical reaction that's generating heat. Right? I don't want to burn the body of the boiler that it's in. So I have to make sure that the materials I use for the body of the boiler, for example, can allow the heat to dissipate so that the temperature inside the boiler does not exceed a certain value. For example, I'm just giving an example. So in that case, this would be the temperature inside. So this is this here. This is T max here. I don't want this to be greater than a certain value, right? So if this is the case, then I have to design everything around it so that the thermal impedance is within a certain limit. Otherwise, if the thermal impedance is too high, what's going to happen to the max temperature? This is the heat from the chemical reaction. This is the heat from the reaction. This is heat. This is heat from the process, from the chemical reaction. If this heat from the chemical reaction is in an area, a closed area, that has a very high thermal impedance to ambient. So there's a big insulator in it. Is the heat going to go outside? There's a big impedance to heat. So if the heat stays inside, what's going to happen to the temperature inside? Keep rising until the reaction fails or the body of the system or the equipment fails, for example. Right? So you need to be able to design the system accordingly, where you guys will work with the mechanical engineers, for example. Right? So if this is your maximum point, so I want to make sure that Tmax is equal to what? Can Tmax be less than the ambient temperature? Unless you're freezing the system. Assuming you're not freezing, assuming it's a process of generating heat. Then it cannot be less than the ambient temperature. So Tmax will always be T ambient, which is T1, plus what? Yeah, plus the impedance to heat flow, thermal resistance. So you have a certain power loss. This power loss is this heat, this P, right? I'll take this P, multiply it by R. This P is my power loss, okay? And this R is degree C per watt, the thermal resistance. So every watt of loss will raise my temperature by a certain, because this has to be temperature, right? This is T, so then this has to be temperature as well, right? And stoichiometry, one word I remember about chemistry, stoichiometry. Stoichiometry is where you make all the units the same, right? Right or no? It's not? Okay, sorry. I forgot chemistry. What is stoichiometry? But I thought it's when you have to make sure when you balance them, which means all the units are the same. Okay, I forgot. What did you say? Anyway, we have an equation. If you're going to add terms of an equation, that means the units have to be the same, right? If you're going to add temperature to something and you generate a temperature, that means you're going to add temperature to a temperature, right? So this thermal resistance is what? Is the degree of hindering this heat flow. So what is that going to do? This thermal resistance will cause the temperature to rise when? Every time there is heat, there is power loss. So its unit is typically degrees C per watt. Right? So now if I have 1 watt of loss, these losses, power is in watts. Right? So watts divided goes away with watts, and I'm left with degrees C. Right? So if this thermal resistance is 100 degrees C per watt, and I have 1 watt of loss, the temperature rise above ambient will be what? 100, right? So the temperature at my core of my reactor will be my ambient temperature plus thermal resistance multiplied by my loss, right? So here, what do you do? This is an electrical circuit. This is electrical circuit analogy for a heat transfer equation, first order approximation of a heat transfer equation. As an electrical engineer, I have to understand this because I design power supplies, for example, for computers that fit in these boxes, for example, that I need to make sure are going to survive your use of them while you're having fun in the desert in summer, playing a game, for example. So you're playing a game in summer, ambient temperature is 50 degrees Celsius. This laptop has a CD moving, and no more CDs, right? So it has the big screen retina display on, and it's generating all this heat, and the processor is burning a huge amount of power. And so the temperature of the processor is what? The ambient temperature plus the ability of the designer to design the thermal resistance from the processor to the outside to be as low as possible. That's where the mechanical and chemical engineers will come into play. So the idea of circuit analysis is really not merely the quizzes that we're going to take or the hundreds of problems. It's really something that you can actually utilize. And it's something that you can relate to other people, other electrical engineers from other disciplines, how to understand stuff that you're working on, for example. Okay, so we took the example of a power system, where we reduced the power system to a circuit. Nothing but a voltage source and a few impedances in series and parallel. That's a power system. A heat transfer problem. This is a heat transfer problem. A fluid flow problem. I can do the same thing. If I have a source of water and a pump which creates head and some pressure drop through pipes and then a tank that I want to fill, I can represent it the same way using electrical circuits. Right? So the idea of electrical circuits is really something more than what we can do in the course. I hope you see the physical definition, physical meaning behind it. So all of this was to tell you that we're gonna go back to solving DC circuits quickly and what the load matter is doing. But so we will do some DC circuit analysis, which is similar to hopefully a good review to what you guys have done before. And you have to simplify these circuits, so there will be certain theorems that hopefully you've seen some before, and we'll be refreshing them throughout the course. Nodal analysis, Thevenin equivalence, etc. Capacitors and inductors are going to be placed in the circuit. Why? Because they are energy storage elements. An inductor can be like in a fluid example, for example, inductor, for example, can be like, those wheels, the water wheels, that have water in each one of those slots, and they're used to, what's the application of these water wheels, for example, in irrigation application? You have a big pump here, and you're pushing water through a small channel into this water wheel. This pump may be operating intermittently, may be pushing a very high flow rate, etc., etc. If you want to irrigate your farm, for example, with a very nice, steady flow rate, it's probably going to be lossless. You want to transfer all the water through, and yeah, this is why you would need this water wheel, for example, in a farming application. Inductor is the same, right? So you have current flowing through the inductor. What the inductor does, it does not allow the current to change abruptly, like the water wheel. It will not allow the water to change abruptly at the output. So what's going to happen at the output? You're going to take some of the water, which is in one of the storage units, transfer it to the outside. Another unit, transfer it to the outside. So you're going to create a smooth flow of water on the outside with no abrupt changes, because you're filling all of these buckets and pushing them to the output here. And that's exactly what an inductor does. So it's adding a delay in the flow, right? So you put water in, you don't see it right at the output right away. You see it after a while, so there's a delay. The same thing inductor does for current. The current lags or is delayed in an inductor application. So if you push current through, it will not allow current to change quickly. It will change it slowly. The same thing. It's lossless. All the water you push in will be pushed out. Same thing. Current comes in, current comes out. Right? So it stores the water. Same thing. It stores the water and creates what? Inertia for the wheel. Right? This is energy. Right? This is energy that's stored in the wheel. Right? If you turn off the water, the pump to the source, what's going to happen? The wheel will continue because there's an inertia that is generated, that is created, and there's water stored that will keep this wheel turning for a little bit. Same thing with an inductor. As soon as you push current through it, it will create a magnetic field around the inductor. That magnetic field is there, it exists. If I turn off the power, that magnetic field is there. If I put the electrical circuit, connect the electrical circuit there, it will dissipate that energy that is stored in the magnetic field. Right? Exact same. So you look at circuit with capacitors, inductors, and then you look at the startup and stop of these circuits, right? So this is what's called transient response of these circuits. You obviously don't, if the water wheel is starting up, it's very different from the case where the water wheel is already continuous, right? Initially, you're going to have to ramp up the current flowing through it. But then when everything is in steady state, the water flow rate is constant, right? But initially it wasn't, right? So that's what we'll study in the transient circuit response of these types of circuits. So if you keep in your mind that all these circuits are analogies to something you studied in your discipline, you will like it a little bit more. Then we will study filter circuits or filter design. Frequency response. The chemical engineering guys, they do study control, right? You do study control with Dr. Muhammad Munir. So, people who didn't study that yet, control is probably something like a senior level, right? Last course, yeah. So you will get an introduction to frequency response. So, in a system, like any physical system, like a car. In a car application, when you press your foot on the pedal, pressing your foot on the pedal will not automatically bring you from 0 to 100 kilometers per hour, right? Why? Because this car has a certain frequency response. It's a physical system. It has a frequency response, right? This frequency response depends on what? It's a Corolla or a Lamborghini, right? The transfer function will be different, right? The transfer function of the Corolla versus the Lamborghini will be very different. So even though the input is the same step response, same person sat there, put your foot on the pedal all the way, they did it as fast as possible, they use the same input. But the transfer function is different, so the output will be different. So what if we now want to analyze the system and understand it better? We're going to make that person, put his foot on the pedal slowly and do it in both parts. A little bit faster and do it in both parts. A little bit faster and do it in both parts. And then time the time needed for the car to get to acceleration point. And draw that against how fast the person put his foot in the pedal all the way to the bottom. Right? Then we get what? We get the frequency response of the car. The frequency response of the car, we can draw it represent it on a frequency response curve. We call that a body diagram, a body plot, sort of representation of the frequency response of the system. It's the same with the chemical process, same with the mechanical process, thermal process. All disciplines study that, probably except petroleum engineers. They go on the rig and they just drill and stuff like that. The science we take, as long as you don't share that with the petroleum engineers, I'll be fine. But we have the science, and then they sort of took the science and said, okay, we can drill for oil. Okay, mechanical engineers can do design of the stuff, and chemical engineers know the drilling fluids. So we don't really need petroleum engineering, but I think we had to create it. So that, and then, okay, so then we'll study some logic circuits. Logic circuits are the basis of computer architecture. So if you're in chemical engineering, why do you care about that? Because all chemical processes today are controlled by control systems. And actually what's ending up happening is a lot of chemical engineers are going to process control. Right? So once you go into process control, you may actually be the one in charge of designing the controllers responsible for controlling the process. These controllers are actually basically computers at the end of the day. Right? So we will study sort of the basics of digital system design. Not too much, just and this is 0.6. And then if we have time, we'll get into rectifier circuits, which are what is needed to take your AC power and convert it to DC power needed for running your process controllers or running your embedded systems needed to control the car or whatever. And op-amps are another component that is very interesting because you can use it to design amplifiers and filters and stuff like that. So this is the sort of the course content. We will not have graded homeworks as such. I will assign homeworks, and these homeworks will be similar to the other classes' homework. So Dr. Robert and I will be giving the same homework set, which covers the same concepts that we want to make sure that you understand. The homeworks will not be graded. We will share with you the solution the following week, but you will have quizzes in the labs on the homework problems. So we will choose one homework problem, and you will be quizzed on it in the lab. So so doing the homework beforehand is something good for you, so that you are able to grasp the concepts needed, and you will be quizzed on one of the homework problems. If we may change the numbers around. So instead of 5 volts with 10 volts. So but the problems will be the same. The TA for the course is Randa. This is her phone and email address. I put the office hours in here. This is the grade distribution. I forgot to say the class website, sorry. The class website is this one. It's my homepage. If you go to seeclab.com and you go to teaching, you go to Principles of Electrical Engineering. So the website is seeclab.com. I will write it down. seeclab.com is the website, and you go to teaching 215, and then the password for the website is GoECEN 2016. Okay, so that's the password that you will need to put in. So I will upload, as I said, the videos there. They should be there very soon. The grading policy, if the grade distribution is here, as I said, you will have lots of quizzes in the labs. You will have 2 exams, and I've tentatively put the exam dates around the week of 21st and April 3rd. So these are tentatively the weeks that we will have the exams on. It's not set in stone, we may change those. I have office hours, and Randa has office hours. Again, you can come by any time or by appointment. Typically, it's going to be easy to find you. So we'll stop here unless you have any questions. Please go through the rest of the syllabus, and the 20% of the lab is divided up into different sections. So please go through that. There is a pre-lab and the lab report, etc., etc. So it's not too demanding. It's not a 3-hour lab. I think it's a 2-hour lab only. So it should be not too difficult to master. there will be a lab report. There will be penalties for the submission, for late submissions. Quizzes will not be repeated. I'll probably drop the least lowest grade in the quizzes that you will have, but they will, if you miss it, you miss it, unless you have a medical excuse, of course. And then make sure if you sign the lab safety agreement, please, because otherwise we can't let you in the lab. So please do that. So I will stop here unless you have any questions. So, as I said, I will post this material to the class.